In this culminating example, we're going to derive the entire equation of motion for this complex system, with x being the degree of freedom that we want to track in the end. Even though there's a lot of elements all put together here, we're going to see that really there's only a single independent degree of freedom in this entire system. All right, so we are told to put a damper in, so I'll draw it in here so we don't forget about it. So damper C, and that is going to be located halfway up this arm, this L2 arm. So this distance will be L2 over 2. And then I overwrote that, that's L2. All right, so to derive the equation of motion, we're going to use Lagrange's equations for this. We're going to need to find our V, our R, and our T for the system, and then do our partial differentiation to get the equation of motion in the end, that ODE that describes the motion of our system. And again, our targeted degree of freedom is going to be x, that in the end we want to express everything in terms of. So let me start just sketching some diagrams here that we're going to be able to use. So let's look at the bell crank lever and just see how it's put together, and then draw it in its nominal state or its equilibrium state, and then what happens if it's perturbed from that state. We are told here we can assume small angles of deflection, and we are going to have negligible gravitational potential. So that means that the potential energy due to the change in the center of mass of this bell lever is going to, we can ignore that. Also, we're not told where the center of mass is anyway. All right, so this is the nominal state, and now I could rotate clockwise or counterclockwise. I only really need to sketch it in one of those orientations. So what happens from the equilibrium if it rotates counterclockwise? All right, so the small angle of deflection is going to theta. So let's assume here theta is positive. So a theta positive will be defined, just so I'm consistent with everything I do in this problem, I'll define positive theta as a counterclockwise rotation of this bell crank lever. Right, so this point here, if we look at the diagram, our mass M has a rigid cable or a rigid rod, we'll assume, attaching it to the crank lever arm. So this point here is going to move an amount x. It's already defined. It has to move the exact same amount as that mass, with that, we'll assume, a rigid bar attaching them. And because of small angle approximation, we're going to say that it must move orthogonal to that original orientation, so it can only move vertically, or it mostly moves vertically. So that's what x is going to be. And originally this is L1, and this is L2. Now, so the top of the arm is going to move purely to the left, and I also want to include this point here, which is where that damper is going to be attached, and that will also move purely to the left, again due to that small angle approximation. So I have to give some coordinates here. I'm going to call this x2, positive left, and this I will call xc, also positive left. So all these new coordinates that I'm inventing, or degrees of freedom I'm inventing, I can give a name to if it's not already named, and a positive sense of direction too. Now the sense of direction, I could say it's left or it's right. It doesn't really matter as long as I'm consistent, and we'll see when we start relating all of the degrees of freedom to each other that as long as I'm consistent with what I defined as positive or negative, that will be reflected in the relationships I'm going to find between my degrees of freedom with that geometric relationship. All right, so looking at like the x2, for example, this sphere is rigidly attached to the crank lever, so the center of mass of that sphere must also move by x2, and then that's going to be displacing the spring K2. We'll start to see that as we develop the V, the T, the R. But we'll need some more diagrams later, but we can start here. So let's start writing out some of these quantities we need in order to use Lagrange's equations. So I'll just start with V here. So V, the potential energies, we're told we can ignore gravitational potential in this problem, and Oftentimes we will anyway. We'll see later examples where we don't and how it's going to complicate the math, but here we'll ignore it. So what in this system is going to contain potential energy? Well, we have that spring at the bottom, K1. We have a spring horizontally, K2 at the top. We have nothing else in here is going to have potential energy, again, since we're ignoring the gravitational potential. So two terms should go into V, the K1 and the K2. All right, so 1/2 K1, I'll do the K1 spring first. So 1/2 times its spring constant K1 times its deformation. Now the K1 spring on the bottom is attached to the floor, so the bottom can't move, and then the top is connected to M, and M already has a degree of freedom associated with it, X. So the deformation of spring K1 is X, so that'll be X squared. And now I need to account for K2. So K2 is up here. I'll just add to my sketch to remind us this is X2 as I've defined it lower. This is XC as I've defined it. There's going to be this rigid rod connecting the top of the crank to the sphere, and then the right side of K2 is attached to the middle of the sphere and the left is attached to 0. So if the bell crank moves X2, the sphere has to also move X2, which means that the spring K2 has to move X2. So the potential energy in the spring, 1/2 K2 X2 squared. All right, so for now, my V is defined with X and X2. X in the end is what I want everything in. I'm going to hold off, though, on doing my geometric substitutions yet. I'll just put V aside for now. I'll come back to it, though, once we get all those associations done. So let's look at R, the Rayleigh dissipation. In this system, the only thing that's going to dissipate energy is the damper C. The springs do not, the masses do not. There's no friction that we're accounting for here, so only that value of C. So we have to add 1/2 times, well, we're told the damping coefficient is C, and now the relative velocity of that damper. It's attached to the wall on the right, so no velocity there. And on the left, at least the way I drew it on the right, now on the left is attached to XC as its position, which means that XC dot is its velocity. And that will get squared because that's how we account for viscous dampers with the Rayleigh dissipation term. So 1/2 C XC dot squared. So again, it's in a degree of freedom. I ultimately don't want that X sub C term, but for now I'm going to move on and I'll do that substitution later. And now the kinetic energy in the system. So here we do have a lot of terms with a lot of pieces with kinetic energy. So one, we have the mass M that is able to translate vertically only. So that will be one term. We have the crank lever arm with that mass moment of inertia. So one, we are told in the problem statement to assume that it has negligible mass. So that means that we can neglect its translational kinetic energy. And once again, we don't know its where the center of mass even is. So much like how we neglected the gravitational potential energy, we're neglecting its translational kinetic energy as well. However, it does rotate and it does have a non-zero mass moment of inertia. So there will be rotational kinetic energy in the bell crank lever. So that's the second term we're going to have in our kinetic energy. Then we have the sphere. So it can translate because its center of mass can move left and right. So translational kinetic energy. And also the sphere, if we see it's resting on the ground there, and we have this no slip condition. So the sphere, in order to move, must rotate. It cannot just slide. If it could simply slide, it would be just like a mass on a cart or the vertical mass where it would only translate. But we're going to see that the sphere will translate left-right and rotate about its own center of mass. So the sphere will actually have two kinetic energy terms that we need to account for. So we'll start with the easier terms. Let's see, what's the kinetic energy of just the mass m in the system? It's translational, so it's 1/2 mv squared. So 1/2, the mass is just called m, and then its velocity, has a position from its equilibrium point of x, so its velocity is x dot, and that gets squared. And that's it. That's the translational kinetic energy. That's all that mass has. Let's move on to the bell crank lever. Again, it does not have translational kinetic energy, but it does have rotational kinetic energy. So 1/2 times its mass moment of inertia. We're given J naught. We won't calculate it in this case. We'll just assume it's a parameter given to us, times its angular velocity. Well, in this diagram to the right, I've already defined its angular deformation or angular deflection as theta. So that means its velocity is theta dot. And that gets squared. Now we'll move on to the sphere. Again, this actually has two terms in the kinetic energy because it can translate left-right and rotate about its own center. So let's do the translational part first. So 1/2 times the mass of the sphere, we're told to use ms, times its linear velocity, its left-right velocity. Well, the center of mass is rigidly attached to the crank lever, which has a position of x2, so the velocity x2 will also be the velocity, the linear velocity of the center of the sphere. And the last piece here is the rotational kinetic energy of the sphere. So I'm just going to draw a picture over here of the sphere. So this is x2, and I am going to call its rotation about its own center theta 2. And again, we're going to have this no slip that's going to come into play as well. So theta 2 is originally 0. As it rotates, that's going to be the angular displacement of our sphere. So the time derivative is going to be the angular velocity about its own center. So that's going to add 1/2, and we'll call it for right now Js, the mass moment of inertia of the sphere about its own center, times its angular velocity squared, which would be theta 2 dot squared. Right, so we have the building blocks for the equation of motion, but if we look, there's a couple things that we're going to need to modify here. V, R, and T all have degrees of freedom that are not the one desired independent degree of freedom x. I invented this x2, that will have to be replaced. xc, that has to be replaced, and theta 2 has to be replaced, and theta itself. Everything needs to be in terms of x. So there's going to be geometric relationships between all of these new degrees of freedom in x that we have to establish. Also here, looking at the parameters that were given to us, I did invent something called Js, the mass moment of inertia of the sphere. That was not given to us, so I will have to relate that to parameters that were provided. And we'll see how the mass moment of the sphere is going to relate to its mass and its radius. So let's look at some of these geometric substitutions that we're going to need to make first. So based on the crank lever arm, we can relate, since x is in there, like we've done before with similar triangles, we can make some relationships here. So what we can do first is we can use similar triangles. We have this AA similarity between the triangle made of L1 and X, and then the triangles made of L2 and X2, and then remember this was L2 over 2 and XC. So the ratio of X to L1 is the same as the ratio of the corresponding parts of the other triangles. So let's start with X2 over L2. Right, so I want to substitute out the X2. So X2 is going to be L2 over L1 times X. And deriving everything with these algebraic values is nice because now this is going to be kind of the generic solution to any system that looked like this. Once we're told the actual numerical values of the parameters, we could plug those in and we've already solved the problem. I need another relationship. X to L1 is the same as XC to L2 over 2. So L2 over, I'll just put the 2 on top there. Right, so rearranging this, so I'll be able to substitute out the XC, multiply by the L2, so it's going to be L2 over 2L1 times X is XC. So some of our geometric relationships are now established for x2, xc, and theta. But remember, there is still this theta 2 degree of freedom I'm going to need to substitute out. So there's still this another geometric constraint here that I need to work through. And this, we're going to be able to look at the sphere itself. Now, we were told that the sphere had this radius of rs. So this is where the no-slip condition is going to come into play, because we know that the motion of the center of mass is going to be related to the angular displacement of the sphere. So one way we could think about this is if this sphere rotates and does not slip, that means the surface of the sphere must remain in contact with the ground at all times, and the whole circumference of it is going to be touching the ground as it's rolling. So what we could think of here is, well, one full rotation of the sphere is going to mean that the sphere is going to rotate, the entire circumference has to rotate and travel along the ground, meaning that the x2, the distance the center of mass travels in one full rotation, is equal to the circumference of the sphere. So as it rotates, the arc length of rotation is going to equal how much it translates left or right. So we can use a relationship that rs theta 2 must equal x2. So again, thinking about full rotation here, let's say theta 2 is 2 pi, one full rotation. This is telling us that 2 pi times r, which is equal to a circumference of a circle, is equal to x2. And in a no-slip condition, yes, that must be true. One full rotation means that the center has moved by one circumference. So this no-slip condition allows us to relate the rotation of the sphere, angular rotation of the sphere, to the translation of its center of mass. Right? But x2 is not our desired degree of freedom either, but we already know that x2 is L2 over L1 times x. So this lets us relate now theta 2 to x as well. Right? So now theta 2 will be L2 over rs L1 times x. Right, so the no-slip condition gave us the relationship between theta 2 now and our desired degree of freedom. I'll start putting some markers here for the ones that we're going to be using in our substitutions. All right, so all of our new degrees of freedom that we invented because it was convenient for coming up with v, r, and t, we now have geometric relationships for that relate them to that one desired independent degree of freedom, x. So scrolling back up here, all the degrees of freedom are going to be taken care of once we do our substitutions. So the last thing we invented was the mass moment of inertia of the sphere, Js. But that too, we know that for a sphere, we know how to calculate that mass moment of inertia. So if we look it up in a table, for a solid sphere, its mass moment of inertia about its center of mass is 2/5 times the mass of the sphere times the radius of the sphere squared. Right, so that Js, just by knowing it's a sphere and we are given the parameters of mass and radius, we're going to be able to make that substitution in that t equation. So now we can start to rewrite our v and our r and our t. Right, so let's come back up here and look at v. Right, the first term is okay because x is already in our desired degree of freedom. And we have 1/2 k2, now quantity x2 squared. Again, x2 is L2 over L1 times x. So L2 squared over L1 squared times x squared. Now, if we look at v, our only dependent degree of freedom is x. So now I want to rewrite it in this more convenient way. I can pull a 1/2 out in front, k1 plus k2, L2 squared over L1 squared, and then the x squared I can pull to the back. Now that v is rewritten, I can move on and start looking at r. Now I can rewrite that in terms of x. I have the definition for xc below. Remember, since L2 and L1 are constant, I can just differentiate both sides and relate xc dot to x dot. So rewriting this, I have 1/2 times c, And now I need to square xc dot, which is the same as, well, xc dot is the same as L2 over 2L1. So squaring it, I have L2 squared over 4L1 squared, x dot squared. Right, and now R is in the form that we're going to see is convenient for doing our differentiation in the following step. Right, so I have some constant on the inside, I have the x dot squared on the outside, and it proceeds with that 1/2. So now t I can go and rewrite in terms of our desired degree of freedom, x. So the first term is okay, or really x dot for this one. So x dot, that's already in a good place, plus 1/2 j naught. I have theta dot squared. Theta dot is x dot over L1. So I can rewrite that, plus 1/2 ms x2 dot. We know x2 dot is L2 over L1 x1 dot, or sorry, L2 over L1 x dot. So when we square that, we are left with that expression, and that's x dot squared, plus a 1/2 js. Remember, we calculated that based on knowing this is a sphere, was 2/5 ms rs squared. Right, that's just the js term, and we're going to be able to do the replacement also of theta 2 dot. Theta 2 dot is going to be L2 over rs L1 times x, and then that's going to get squared. So we can multiply this by L2 squared over rs squared L1 squared x dot squared. L2 over rs L1, everything gets squared there. Right, so looking here, we have an rs squared on the bottom, and on the top I can eliminate those, and actually the RS's are going to go away. The t, I can now pull out the 1/2, and notice here I have a 1/2 and I have a 2/5 from the JS. I don't want to cancel that out because I actually want the 1/2 in front of everything, so that now in this step I can factor out the 1/2. So what am I left with? I'm left with an m plus a j naught over L1 squared from that second term. The x dot will go to the outside, plus the 1/2 is on the outside. I have an ms L2 squared over L1 squared. X dot will go on the outside, plus that 1/2 I took to the front. So I'm left with here a 2/5 ms L2 squared over L1 squared. Remember the rs is canceled out. And then the x2 dot is on the outside. And I can actually clean this up just a little bit more, because we'll see that those third and fourth terms I can combine now. I have a 1 ms L2 squared over L1 squared plus a 2/5. So 1 plus 2/5 is going to be 7/5 when I combine it. So effectively, by that sphere being able to rotate as well as translate, effectively it has more equivalent mass in our system, because there's two modes for it to contribute or take kinetic energy. Right, so it's 7/5 instead of 1 if it couldn't rotate. All right, so with all that, t is now rewritten, and it's in the form we want. So one more quick look. So v is now only in terms of our x, r is in terms of our x dot, and t is in terms of our x dot. And all of our coefficients have only parameters that were given to us. So at this point, we are now ready to derive our equation of motion by using Lagrange's equations. So if we go down here, the general form, again, we're going to use is this d dt of del t del x dot. X dot is the derivative of our chosen independent variable. Now it's technically, I'll write it out here, del t del x plus del r del x dot plus del v del x equals 0. So quickly looking at our t expression, we have an x dot term, we have no x terms, so this term is going to go away. This term will be 0. So I'll just make sure that we're clear on that. And typically that will be the case. It will be equal to 0. But for good measure, I included it just in case it didn't. All right, so let's see what we have here. So we want to take the partial derivative of t with respect to x dot. Well, conveniently, I've already written this in a nice way. So when I differentiate with respect to x dot, that 2 is going to come out in front and cancel the 1/2. So I am going to be left with m plus j naught over L1 squared plus 7/5 ms L2 squared over L1 squared x dot. Now that's just the del t del x dot. Now I need the time derivative of this. The only thing affected by that is x dot goes to x double dot. All right, so that is my first term. Now, del r del x dot. Again, it's already written in a really convenient way. When I differentiate with respect to x dot, it's going to cancel out the 1/2, and x dot squared goes to x dot. So what I'll have left is just the stuff on the inside here. So I'll be left with this c L2 squared over 4 L1 squared x dot. Oh, and just as a reminder, it's 0 on the right-hand side here because this is an autonomous system. There is no forcing involved, so the f is just going to be 0. And now del v del x. Once again, the way I was able to write v, x squared is going to go to x, that 2 is going to cancel the 1/2, and I'll just be left with the stuff inside. So what's left inside is a k1 plus a k2 L2 squared over L1 squared x. Getting a little cluttered here, but that's equal to 0 then. As a reminder, that was the stuff inside the parentheses, that coefficient in the middle. Okay, so this is now, with just a little bit of indication here, this is my MEQ. So my equivalent mass in this system is the coefficient in front of the x double dot. This is my CEQ, and this is my KEQ. So I can rewrite my whole expression now that I know the equivalent mass, equivalent damping coefficient, and equivalent spring constant. I'll drop the EQs just for this. So this is what my equation of motion looks like. Right? And with these m's, c's, and k's that I have above. So the whole purpose of this modeling work was to, well, the end result is getting this equation of motion. Looking at this equation of motion, I know from the 0 it's autonomous, or it's a free system. There is an x dot term, so it's damped, and it has an x dot, and x double dot. It's linear, and it's second order. And really, this is generically what undamped free vibrating systems, damped vibrating systems are going to look like in general. The question we get, the answer we get out of the modeling is, what is the m, the c, and the k? Well, that's what we have above. So this is the equation of motion here, but specifically with these values of m, c, and k put in there. So that is the complete equation of motion for this system.